Welcome to a screencast on the last little bit of solutions. First of all, here's the problem we did in class on Wednesday. And I'm going to go through this very quickly since we already did it. To find molar mass, we need to get moles and grams. Moles are within the osmotic pressure relationship, so we solve it for moles and plug in our values. Make sure you convert the pressure, osmotic pressure, to ATMs. Volume has to be in liters. We use the gas constant in liter atmospheres per mole Kelvin, and temperature has to be in Kelvin. And then, because this is a molecular compound, bovine insulin, it has a Van 't Hoff factor of 1. Do the calculation. We get 1.67 times 10 to the minus 4th moles of bovine insulin, our solute. And then the molar mass is the grams of solute per mole of solute. And that works out to be 6,000 grams per mole. And this is a 2 sig fig answer because our osmotic pressure was 2 sig figs. So we're going to round that to 2 sig figs, which is 6.0 times 10 to the third grams per mole. Very big molar mass for a big protein like this. Okay, now we're going to pick up the questions that we skipped over previously, and a strong suggestion: pause before you look at the answer. Pause the screencast and see if you can figure out what the answer might be. What's the key concept? What do you have to do? What do you have to think about? What do you have to calculate? What's the equation to use? And that sort of thing. So pause, see if you can figure out how to arrange the following from lowest to highest freezing point. Okay, so I hope you've paused. I hope you thought about it a bit and came to the conclusion that if we make a solution, these are all aqueous solutions, except for the last one, which is the pure solvent water, then their freezing point will be lowered, and their freezing point is lowered according to the relationship that we've seen before. Delta T, how much the freezing point is lowered, is equal to the freezing constant times the molality times the Van 't Hoff factor. So for C6H12O6, a molecular compound, 0.25 molal of that has a what we'll call an effective molality, also of 0.25, because each glucose molecule does not break apart into pieces. It has a Van 't Hoff factor of 1, so the molality times the I value gives you 0.25. That's the molality of particles in the solution, and that's what affects the freezing point. Now, CaCl is 0.2 molal. That's a little smaller concentration, but CaCl breaks apart into K plus and Cl minus, so it has a Van 't Hoff factor of roughly 2. So 0.20 molal times the Van 't Hoff factor of 2 gives us an effective molality of about 0.4 in terms of particles, and that's bigger molality, so we'd expect that to have a bigger freezing point depression. And then the Na2SO4 is even lower in its nominal concentration, 0.5 molal, but each Na2SO4 breaks apart into 3 pieces. There's a sulfate ion and 2 separate sodium ions. So the effective molality for 0.15 molal sodium sulfate is 0.15 times roughly 3, which is 0.45, and so that has an even bigger effect on the freezing point. So if we put them in order from lowest freezing point to highest, water is going to have the highest freezing point because its freezing point isn't affected, and then the lowest freezing point will be the sodium sulfate, then the CaCl, then the C6H12O6 in terms of highest effective molality, and then to increasingly less large effective molalities. Okay, now question 14. We didn't do this. It's a vapor pressure calculation. We want to find the vapor pressure of a solution that contains 50 grams of acetone and 50 grams of ethyl acetate. And note, we're given the vapor pressure of each of these, acetone and ethyl acetate, at that temperature we're interested in, 30 degrees Celsius. And both of these have vapor pressure, so they're both volatile substances. So to get the vapor pressure of the solution, we actually have to do our vapor pressure equation we've seen before, but for both substances. So acetone and ethyl acetate, both of those are volatile. So both of them contribute to the vapor pressure. And they contribute to the vapor pressure depending upon what temperature they're at, which is the same for both, of course, and depending upon their respective mole fractions. So the equation is the vapor pressure for both substances total is the P times X, the vapor pressure of pure acetone, times the mole fraction of acetone. That's the vapor pressure due to just the acetone. And then we also have to add the P times X, the vapor pressure of the ethyl acetate, times its mole fraction. And so that gives us the contribution to the vapor pressure of the ethyl acetate. So should be pretty easy to convert grams into moles. Acetone is 0.861 moles. Ethyl acetate is 0.568 moles. So when we plug in our numbers, vapor pressure of acetone is 285 torr. Moles of acetone is 0.861. Total moles is moles of acetone plus moles of ethyl acetate, 1.429. And then we do the same thing. We add, we do the same thing for the ethyl acetate, and we add that. So the vapor pressure of ethyl acetate is 118 torr, and then there's 0.568 moles of the ethyl acetate in 1.429 moles total. Moles will cancel, torr will not, so we'll get a vapor pressure due to the acetone, we'll get a vapor pressure due to the ethyl acetate. When we add the two together, we get 219 torr. This should make some sense. It's lower than the vapor pressure of the pure acetone. It's higher than the vapor pressure of the ethyl acetate, so a mixture you kind of expect to have a vapor pressure that's in between those two. So that's how you deal with vapor pressure. If you have two volatile substances mixed together, you do the vapor pressure equation for one, the vapor pressure equation for the other, and then you add them up. Okay, is acetone or ethyl acetate more soluble in benzene? I looked at this again and I realized this is not a real good question for this level. We're going to omit it. It's a pretty, normally you'd be looking at intermolecular forces and like dissolves like, but here it's kind of a tough call, and so I'm just going to say let's skip that one. Okay. Draw molecular level picture of representing a mixture of calcium chloride and benzene, C6H6. This we should be able to do. Benzene is a molecular compound. It's going to be very nonpolar, a 6-membered carbon ring. Calcium chloride is an ionic compound, positive ion Ca2+, and 2 negative ions Cl- and Cl-. If it dissociates, we'd expect we'd need at a minimum polar solvent to have that happen, and benzene is not. So we're going to simply have some benzene molecules, and we're going to have some calcium chlorides that stick together and pile up on the bottom and don't dissolve in the benzene. So our mixture really will not be homogeneous. We'll just have calcium chloride on the bottom, benzene on the top. Okay, question 15. And again, remember, think about this ahead of time. See if you can pause and try to answer this before you look at the answer. So I'll give you a chance to pause. Okay, and now we're back. Let's look at this. We have a freezing point depression of sulfurous acid 1 molar solution compared to water of negative 2.01 degrees Celsius. We're trying to find the Van Hoff factor. We know the molality. Normally we determine the Van Hoff factor. We look at the substance and say, oh, it breaks apart into so many pieces. But you might note H2SO3, there's kind of an implication here that maybe we don't know how many pieces that breaks apart into. And if you think back to Chem 1A, we talked about acids, of which sulfurous acid obviously is one, and how we would treat that in terms of its dissociation and it being a strong acid or a strong electrolyte. So let's see what we get here. Well, we can solve this for I, pretty straightforward. And then we plug in our delta T is 2.01 degrees because negative 2.01 is 2.01 degrees Celsius lower than 0. The K sub F is a known value we've used a bunch of times, and then 1 molal is the molality. And we calculate and we get 1.08, so a little bigger than 1. So what does this mean? Well, if it was 1, then we'd say the H2SO4 doesn't break apart into pieces. It's a non-electrolyte. It does not dissolve into particles. But it's a little bigger, and so this seems to imply, in fact it does tell us, that H2SO3 does dissociate a little bit. It breaks apart slightly. It's what we'd call a weak electrolyte. It lights the light bulb if you try to test conductivity, just barely. And we could represent it, this is kind of simplistic, and we'll see in a bit, this is maybe not the best way to do this, but H2SO3 has 2 hydrogens that could just dissociate. Then there's a sulfite ion, a SO3 2- as well. And I have a small arrow to the right indicating that only a little bit of the H2SO3 dissociates into the H plus and SO3 2-, and most of it, I got a big arrow going to the left, most of it stays associated. And we'll go into this in much more detail in a future chapter. Okay, worth pointing out, actual values of Van Hoff factor for electrolytes. Sucrose, a molecular compound, has an ideal Van Hoff factor of 1. It's supposed to only or not break apart into pieces. And if we do measurements, kind of like the previous problem, we find that whatever the molality is, 0.001, molarity, sorry, 0.001, 0.01, and 0.1 molar, sucrose pretty much just always does not break apart into pieces, or at least not appreciably. Now, sodium chloride ideally breaks apart into 2 particles, but notice the actual Van Hoff factor is a little less than 2, and it gets more and more less than 2, or farther away from 2, the larger the concentration. And that's because as the concentration gets bigger, there's more likelihood of any given instant an Na plus and a Cl minus not really being separated, and so maybe 18 or 19 out of every 20 pairs are separated, but 1 or 2 perhaps are stuck together at that moment, so they effectively behave as one particle. And this is a pretty common thing. We're not really going into this in detail in this course, but the ideal Van Hoff factor is in reality, with a solution that has appreciable concentration, can differ significantly. So potassium sulfate, ideal Van Hoff factor of 3. A 1,000th molarity solution has a Van Hoff factor of 2.84. Make it a 10th molar. Now the Van Hoff factor is down to 2.7. And even a 0.1 molar solution has an effective actual Van Hoff factor of about 2.3. So this really isn't effectively 3 particles. It's really, well, more than 2, but less than 3 at any given instant. AK plus and an SO4 2- are temporarily stuck together and don't count as 2 separate particles. And again, we won't go into those great gory details other than mentioning it here, just to kind of show you how the real world differs from the idealized version. Okay, and one more to go. Aqueous solution has a normal boiling point of 1.7 degrees above what pure water boils at. What's its normal freezing point? And notice we're not given anything other than the normal boiling point of the solution. So it kind of seems like maybe we don't even have enough information. How can we answer this? So pause again, think about this, write down what relations apply, what you're thinking, what you know, what you're trying to find, and see if you can come up with a way to get to the solution. Okay, so we're back, and there, hopefully you'd say that's the freezing point equation, and we'd like to determine delta T sub F, then we'll be able to get the normal freezing point of the solution. There's the boiling point elevation equation, and we know the delta T, and we can look up K sub F, we can look up B, but we don't know anything about the solution. We don't know its molality, and we don't know its Van Hoff factor. So how do we do this? Well, notice we have two equations and we have two unknown things, and there's a bunch of ways one can potentially do this, but if you have an equation and another equation, you can divide the equations and you still have an equation. Now, how does this help us? Well, how does the molality of this solution in terms of boiling point calculation compare to the molality of this solution in terms of freezing point calculation? Well, it's the same solution, so they're the same. And if I ask you the question about I, you'd have to answer the same thing. So effectively, the M times I cancels out, and we get delta T freezing over delta T boiling equals Kf over Kb. So the ratio of the freezing point changes is the same as the ratio of the respective freezing and boiling constants. So let's solve this for delta T sub F and plug in our known numbers, and we get about 6.2 degrees. And note, this is our delta T. The question asks, what's the normal freezing point? Well, it's aqueous, so water has a freezing point of 0 degrees Celsius, and then the solution will be 6.2 degrees lower than that. So the freezing point of the solution will be negative 6.2 degrees Celsius. And that is it for the wrap-up of solutions.